And then finally, the most accurate method, and that method that has developed the most over the history of space flight, are star trackers. You have some catalog of stars, and you have a camera that can identify, oh, I see these 5 stars. I match them to the catalog, figure out, how it's oriented. And if they're oriented in a particular way, I know approximately, where I'm pointing.
Welcome to another episode of the Mapscaping Podcast. My name is Daniel, and this is a podcast for the geospatial community. Today I'm talking with Jack Reid. Jack is a PhD student at the MIT Media Lab, and today on the podcast we're talking about how to keep your satellite pointing at Earth. It turns out this is a non-trivial problem, but I'll let Jack go into that in more detail in just a second. So I'll be back at the end of this episode to point you towards some more resources that you might find interesting. But first, here's a quick word from our sponsor. This podcast is sponsored in part by Lightbox. So you can find Lightbox at lightboxre.com. And what do they do? Well, Lightbox is a data platform, and it's an authoritative source of North American real estate and location intelligence data. So you're probably wondering, what kind of data are they an authoritative source of? So they have parcels, building footprints, administrative boundaries, census data, schools, demographics for neighborhoods, points of interest, school ratings, traffic volume for neighborhoods. As far as the property side of things goes, they have ownership information, loan and sales transactions, contacts and mailing addresses, historical aerial photography. So you can use the Lightbox platform to do your analysis in the platform itself, or there's a set of APIs that you can use to get a hold of the data that way and perhaps build your own analysis around it, or you can bulk download these data sets as files. If you're looking for a real estate information and technology platform, check out Lightbox. I'll put a link in the show notes to make it a little bit easier for you to find. Thanks, Lightbox. Really appreciate your support. Hi, Jack. Welcome to the podcast. It's a real pleasure to talk with you again, and I'm really looking forward to this conversation. So you answered a tweet. I tweeted out a couple of weeks ago something along the lines of, like, I understand how we orientate sensors. So let's think about a camera, the point of view of a camera, that we need these 6 degrees of freedom. And it got me thinking about satellites. How do we orientate satellites? And so this was my question on Twitter, and you answered it brilliantly. And you had all these points. I reached out to you, we had a conversation, and you taught me so much about satellites, how they orientate themselves in space, how they navigate in space, and a million other things. So welcome to the podcast. I'm looking forward to diving into all of this stuff with you, and I hope that the listeners find it just as interesting as I did. Before we jump in there, would you mind just introducing yourself, please, to the listeners?
Yeah, of course. First off, howdy. So it's a pleasure to be here. Yeah, so right now I'm a PhD student at the Media Lab. By background, I came out of mechanical engineering, did shock and vibration testing at Sandia National Labs before moving fully into aerospace engineering at MIT. Did a master's in aeronautics and astronautics, simultaneously to a master's in technology and policy, sort of getting that policy side of things as well as the engineering. And then for my PhD, I moved into the MIT Media Lab, which is it's a very interdisciplinary space. And I'm very much still bringing that engineering, aerospace engineering background to bear. Some of my lab mates in my research group, which is called Space Enabled, they come from other domains of, ethics or art, other aerospace engineers, data scientists, that kind of thing. We all work together on sort of making space sustainable and using space to help promote sustainability on Earth.
That would explain how you know so much about satellites.
I've been fortunate enough to was exposed to satellites actually my freshman year in undergraduate there's an undergraduate group at Texas A&M University called the Aggie Sat Lab that sort of designs and builds satellites. And that was my initial exposure to it. So it's been quite some time now.
You're talking about your master's in aerospace engineering. And this might be a really naive question, but aerospace engineering, are we immediately talking about satellites, or could this be a range of different things that you're studying?
The department has like a range of different things. Some people do more on the robotics side. Some people do aviation, aircraft. Other people do, launches, launch vehicles, propulsion, and other people do satellites. So it's a sort of a mix. I would say like the cleanest distinction is there's sort of an air side and a space side. And I was very much on the space side of things.
What attracted you to the space side of things? Like, I understand a lot of people, grew up watching Star Wars or whatever, or just have a look up, and look at the stars and are fascinated by that. Is that what the initial attraction was to you when you thought about aerospace engineering and building satellites?
I'm somewhat unconventional in that space was never sort of like a priority for me as a kid. I was interested in a lot of topics. Space was amongst them. I thought the space shuttles were awesome. I thought the International Space Station was wicked. But it wasn't, the first and foremost thing in my brain. I think I actually came about it more through the defense side of things. I have a lot of family in the United States Air Force, so even though I wasn't going that route, it was sort of easy to follow that path. And so, I did some work for Sandia National Labs. I did some work for the Rand Corporation, and that sort of led me more to space. And then the more I started learning about, the details of that through my education, the more I fell in love with, yeah, both space hardware, software, its applications. And increasingly I thought that like, oh, where the real gain is not on the defense side, which I've moved away from, but is on using, space-based assets and imagery for sustainable development. And I've really fallen in love with that aspect of it. Over the course of my career, I've sort of touched on different parts of it, sort of the design and building of satellites, some of the policy and acquisition side on like the defense side of things, and now to using the data that they produce.
When I think about space, I'm pretty sure I think about it differently. So I think about, sure, it's hard to make a satellite, and yeah, we've got to fling a big lump of metal into the sky. But it seems to me like once it's there, it's there. The orbit is stable. It's looking down at Earth, and it'll just go round and round and round, and send data back to Earth. I realize this is a massive oversimplification, but can you tell me where I'm wrong, where I'm oversimplifying things?
Yeah, well, I think that satellites, something that people should keep in mind is satellites, they're very active things. They're not just passively taking imagery or broadcasting messages. They do have various means of moving themselves around, both, sort of in three dimensions, as well as orienting themselves, which is called attitude adjustment. And this is a major contributor to the lifespan of satellites. If those things break, they drift out of orbit or they start looking in the wrong place.
Okay, so let's start with this idea, looking in the wrong place. Isn't that something that's decided when the satellite is shot into space, when it achieves the right orbit? Isn't that just a one-time adjustment? Okay, I'm looking down at Earth now, and now I just continue in my orbit.
Yeah, so that's a very good question. And the fact of the matter is though that in space, it is a vacuum. By and large, things are not pushing you around, things are not pushing you in any particular direction. And that includes which way you're pointing. So I know the intuition is to assume that the satellite is going to keep pointing down. But if you actually think about it, the satellite's going to just keep pointing in the same direction. So if it's looking at Earth at one particular moment, as it orbits around the Earth 180 degrees, it's now going to be looking directly away from Earth. And then as it comes back around, it'll be looking at Earth again. So in order to keep looking at Earth constantly, which most Earth observation satellites want to be doing, you do in fact have to continuously rotate it. This is basically actually what the moon does, right? Like we know that the moon has days and nights, and it also has a side that is always facing the Earth. And that's because, its day is the same length as the time that it takes to go around the Earth. But it is in fact rotating about its own axis during that time. So we have to do the same thing with satellites if we want to have them continually pointing at Earth.
It seems to me the first job there is to know where Earth is, like the right direction to point.
Exactly. So you need to know where Earth is and you need to know which way you're pointing. So this comes into there's a subsystem on basically any satellite called ADCS, which stands for Attitude, Determination, and Control System. Attitude being the way that you're pointing, and then determination, of course, is that part that you were just asking about. It's figuring, where's a satellite pointing, where is the Earth, that kind of thing. And there's a variety of sensors that can help out with that. Basically, something that all satellites have is an IMU, an inertial measurement unit, which are basically a bunch of accelerometers and gyroscopes to tell how is that satellite accelerating. There's one of these in your phone, and it's what tells your phone, when to, flip the screen to profile or landscape kind of thing. So that can help keep track over time. But the problem with those is you need to know where you started from, since they only measure basically sort of changes. And the other thing is that since they work by integration, they're measuring acceleration. You have to integrate that to your angular velocity, and then you integrate that again to get to your angular position. And errors creep in at each of those steps, and they build up over time. So this is why aircraft they don't rely on just IMUs, for instance, but these are what you use from moment to moment to tell which way you're pointing. So then you have to have various sensors on top of that to help periodically reset your error down to zero to recalibrate the IMU. And there's a lot of ways of doing that. You can, listen for, radio communications from like known ground stations on Earth. You can have what are called horizon trackers, which basically look at they're infrared cameras that look for the cutoff of the Earth's horizon and space. Because as you might imagine, the Earth is warmer than space is. So by looking at that horizon, you can figure out at least, one thing to point at. It doesn't tell you where on your horizon you're looking at a time, but that's a sensor that you can use. Another one is a sun tracker. Very similar. You just look for the hottest thing in the sky. The nice thing is, the sun, it's not like the Earth horizon where, there might be a full circle of horizon that you can see. The sun tends to be a particular spot in the sky that you can look at. And then finally, the most accurate method, and that method that is developed the most over the, the history of space flight, are star trackers. Where you have some catalog of stars and you have a camera that can identify, oh, I see these 5 stars. I match them to the catalog, figure out, how it's oriented. And if they're oriented in a particular way, I know approximately, where I'm pointing.
So when you talk about the star tracker, the catalog of stars, the map of stars, I guess we could call it. Obviously, we have to identify someone there, and then we can figure out, like you were saying, where we're pointing. It sounds like perhaps doing some triangulation of some description. Is this like the modern day or the space version of the sextant that we're actually talking about?
Yes, it is exactly that, and in fact, it develops. During the Mercury through Apollo missions. They were in fact using sextants, looking out the window. It was not their only means of attitude determination, but it was definitely a means that they used and practiced with, of manually looking out the window, sighting particular stars, writing down their angles, and then doing the trig to figure out which way they were pointing. And then just over time, we've gotten better at automating that. First designing star trackers to keep a lock on just a handful of very particular stars. The downside with that is if you get your camera off from those very particular stars, you might have a hard time getting it back to them. Up until nowadays, where we have much larger catalogs that can be much more easily used to figure out, wherever you're pointing, no matter where your satellite is.
Is that would that catalog, would that be specific to the orbit that the satellite was on? And so I'm thinking that the orbit must be known before we shoot the satellite into space. Would I load it up with a specific catalog or just have all of the stars in there?
That's a good question. I'm not entirely sure how specific they get. It definitely, does matter to a certain extent where you are. For instance, we don't necessarily use star trackers in exactly the same way for, sending missions to Mars or Jupiter or that kind of thing. There are people working on, ways of improving those kind of trackers in the future for those applications, particularly using pulsars, which are much more identifiable. But yeah, you do have to have some knowledge of where you are, in the universe to be able to use star trackers for sure.
I want to go back to the sun tracker that you're talking about because it seems to me if I was looking at the sun, like identifying the biggest, brightest spot in the sky in space, yeah, I could identify that. I would know I was pointing at that, but I could still rotate around one axis at least.
For sure. That's a really concern. And that's why you commonly combine multiple of these trackers or multiple of these sensors to, yeah, to sort of work off one another, to check each other in different ways. Another issue with the sun tracker is it's not as precise as a star tracker. The sun is still it's a fairly large, bright, hot thing in the sky. So if you're pointing, just a few arc seconds off of, center of the sun, it can be hard to tell. So you'll compound them with other things. Another sensor that I failed to mention earlier is a magnetometer, which is this only works if you're in Earth orbit because Earth has a magnetic field. It doesn't work around Mars, for instance. But you can basically measure Earth's magnetic field, and if you have a general picture of Earth's magnetic field, that can also help orient you, which way's north essentially. And so by combining these, combining a magnetometer, a horizon tracker, a sun tracker, star trackers, by combining some subset of those, you can start to get all three of your angular axes and at pretty high precision.
It's interesting. We're sitting here talking about this thing as if it like of course you could just do that. But I was thinking about the magnetic field. Like I'm pretty sure that it's relatively uneven and constantly changing. So it must be a difficult thing to use something like that to figure out where am I with relation to the Earth? Am I pointing at the Earth based on the something that's dynamic?
Yeah, and that definitely feeds into the different accuracies of these. Like I said, a sun tracker is less accurate than a star tracker. Magnetometers are less accurate than sun trackers typically. We do try to keep a pretty up to date map of Earth's magnetic field. There are, both satellites and ground based sensors that do precisely that. But, as you said, it does change pretty rapidly and not necessarily in the easiest to predict ways. And it's highly dependent on what orbit you're in. So that was another, part of you saying, don't you need to know precisely where you are? And yeah, if you need to have some general idea of where you are when you're, measuring these magnetic fields. So yeah, it's definitely not something that people typically rely on solely.
Okay, so it sounds like we're using a combination of all these things, but I'm assuming anyway there must be some sort of trade-off between weight and power consumption. Like a lot of these things sound like they require some sort of power consumption, some sort of computing to figure out, am I still looking at the sun, for example? Where are the stars, with regard to where I am? What stars can I see? That kind of thing. So there must be a few trade-offs here. And I'm assuming that perhaps different combinations of these things are used dependent on the height of the orbit or the accuracy needed for the specific satellite that we're talking about?
Yes, for sure, right? There's definitely a trade-off, right? So things like, a horizon tracker or a sun tracker, and even like a basic magnetometer, you can even make these with analog circuits. You don't even need to necessarily use computers, although all modern versions do. But, so you can do those with, very little bandwidth kind of thing. But when you get up to, a star tracker, it has to be doing trig, it has to be figuring out, what's the most likely set of stars that it's looking at right now. That requires more computational power. And, often it requires, better optics, which means more weight. So there's definitely, these size, mass, cost comparisons that are going on whenever you're designing these kind of things for sure. And yeah, you definitely see regimes where, some are more common, horizon trackers, were more common if you're in a lower Earth orbit, right? Because the horizon's going to take up, a bigger part of your field of view. It's much more of a thing to lock onto. If you're up in, geostationary orbit, the Earth is actually a much smaller, part of your field of view. So maybe it makes sense to use other things. And then also, another trade-off is if you're in a low Earth orbit, so here we're talking, in the couple hundred kilometers up to about 1,000 or 2,000 kilometer range, you're spending a good chunk of your time in shadow. You're going around the night side of Earth, right? Can't use a sun tracker if you can't see the sun. Well, if you're up in, a geostationary orbit, which as compared to the, the couple hundred to, 2,000 kilometer range, geostationary satellites, they're up at about 35,000 kilometer altitudes, way higher. The amount of time that they spend with, the Earth blocking the sun is, way less. So they could much more easily rely on a sun tracker being available all of the time.
Yeah, when you talked about going through the shadow of the Earth, so around the dark side, depending on what orbit you're in, if you're in a lower orbit, it made me realize that I guess it's also really important to know where your solar panels are pointing as well. If they're the things that are powering the satellite, so it's one thing to, obviously, it's really important to know where the sensor's pointing, but it must be equally as important to know how to rotate your solar panels to get the most energy possible.
Yes, that is actually, perhaps the most important for most satellites, right? People who work with maps and with geospatial data, Earth observation imagery is, our, most direct connections to space. But, the vast majority of satellites, they're not Earth observation satellites, they're doing other things, but pretty much all of them have solar panels. And so, pointing their panels at the sun at all given times is how they get power. So you have to do that. You also have to make sure that you're pointing your communications in the right direction. It's pretty wasteful and in terms of power and in terms of mass to have, high powered omnidirectional transmitters and receivers. So a lot of times, they both the transmitters and receivers do need to be pointed to a certain degree at, ground stations, at other satellites. And then finally, of course, you have your Earth observation, which needs to be pointed, at Earth, right? Thankfully, you do have, three axes to work with here, but, sometimes there have to be compromises, and this all definitely has to be thought of when you're designing the satellite and putting these on different orientations. You don't necessarily want your solar panels on the same side of the satellite as the camera that's supposed to be looking at Earth, right? Because then you sort of messed up and you can't point both at the Earth and at the sun all of the time.
That makes perfect sense. It's making me realize how computationally expensive this must be to figure all this stuff out constantly. And I've just recently heard of this idea of edge computing. So my understanding of edge computing is computing that's done at the source, so at the sensor. And I've heard people talking about this in terms of space platforms as running algorithms on data. Let's say images, for example, deciding if there's too much cloud in the image, let's not send it down to Earth. But I guess in reality, we are computing on the edge in space right now. We must be in order to make some of these calculations and make the adjustments appropriately.
Oh, for sure. Yes, that has been typically the ADCS, it has its own dedicated, computational power. Nowadays, with satellites that are getting more integrated, sometimes you see some of these things being combined. But historically, that was probably the majority of your computational power was being dedicated towards determining where you are and where you're pointed and making sure that all of that works. And when you go back to the earliest days of satellites, they would go to efforts to try to minimize the amount of computation there, because of course, it was, very difficult to put computers in space to make them small enough for that kind of thing. And so you would see things like spin stabilized satellites, where this is basically you have a satellite with a camera pointed at Earth, and then it would be you put it into a spin about the axis that is looking down at Earth to help keep it stable, help keep it pointed in the same direction. Because if this is just sort of If you have a high angular momentum, you're more resistant to being pushed around and being turned in different directions. And so doing something like that, adding some more stability was a way of, cutting down on your need for constantly controlling your attitude.
As far as I understand anyway, what we've been talking about up until now assumes that something is pushing the satellites around, that this orbit isn't stable. That obviously, when you were talking at the start, if it's pointing down at Earth, we've got to rotate it. So that's part of the problem. But it sounds to me like there's other forces at work here that we need to adjust and account for. One thing that springs to my mind anyway is there any kind of atmospheric drag, perhaps on the lower orbiting satellites, that is affecting the satellites as well? That means we have to, take that into consideration when we're trying to figure out how to keep the satellite pointed at Earth.
Yes, you are exactly correct. Yeah, in high school physics or whatever, when you're learning about Keplerian orbits, you're typically thinking two bodies that are in a vacuum, and you get these nice, perfect ellipses and parabolas and everything. Nothing to push you off orbit, nothing to change your direction. But you're right. In the real world, there's a lot of other factors, and in low Earth orbit, in particular, drag is certainly one of them. This is where most Earth observation satellites are in this regime. It's where the International Space Station is, all in this few hundred kilometers up to about 2,000 kilometers. And particularly when you're under 1,000 kilometers, you're feeling some real drag. And you need to use propulsion to periodically, reboost your orbit back to where it's supposed to be. The International Space Station has to do that regularly. I think they have to do it almost about once a month or something. So if you don't, you'll drag will catch up to you. It'll slow you down and pull you out of orbit. And that's exactly actually part of why low Earth orbit satellites, have such relatively short time periods, or lifespans. They're commonly measured in years to, like a decade kind of thing, if they're not actively using propulsion, as opposed to, go out to geostationary and those things, they're going to be up there for a millennium at least. And drag is a huge part of that. And drag also it affects your orientation, not just your orbit, not just your altitude. As you might imagine, same thing as if you're driving down the road and stick your hand out the window. If you put your palm forward, you're going to have a lot of drag. Wind's going to try to turn your hand. And then if you sort of put the edge of your hand in the direction of travel, much lower resistance. And that's a much more, stable position. The atmosphere does that to satellites. It's going to want to sort of orient them into the minimal drag position if it can. And you have to have systems on place to resist that kind of thing.
So I guess it's one thing to detect that these things are happening. It's another thing to have the power to constantly adjust. You talked about the International Space Station needing to be boosted back into orbit or to boost it up again to maintain the orbit. So I'm guessing we're needing some kind of fuel on board. Is the lifespan of a satellite in some regards determined by how much fuel it can carry? And is there any way to refuel a satellite?
So yes, to your first question, the fuel is commonly the most significant determinant of the lifespan. If nothing breaks, if nothing goes wrong, your satellite it can keep trucking. But if you run out of fuel, your orbit's going to start drifting. Even if it doesn't deorbit you, it might move out of where you need it to be. Right? If you are relying on a really precise orbit for imaging or for communications, get too far off of that, your satellite isn't any good to you anymore. And really, the only way to move sort of significantly in three dimensions is with fuel. Then in terms of refueling, like you said, this is a thing that we are actively working on. It's been done, here and there a couple of times. It's not something that is regularly done, except for the International Space Station, which we routinely refuel. But there are companies out there that are actively working on that and actively figuring out, what's a good way of getting fuel to satellites in a consistent and easy way to extend their lifespan.
It's kind of amazing when you think about it. Like all of this is happening, all this while the satellite is sort of slowly falling towards Earth. It's incredible. It's kind of mind blowing.
Yeah, for sure. And drag isn't the only thing that affects satellites in this. Like we said, when you think of orbital mechanics, you're typically thinking of just two bodies. Obviously, the satellite and Earth are not the only two bodies that are out there. You got other satellites, you got the moon, you got the sun, you got factors on Earth that matter. So that Earth is not a perfect sphere. It doesn't have uniform density. It's fatter around the equator, kind of thing. All of these can mess with your orbit over time, cause it to shift in one way or another and change shape. And, all those things are things that you got to counteract with some kind of propulsion in terms of, translation or in terms of, some way of changing your attitude in terms of, where you're pointing.
So getting back to this idea of orientating satellite in space. So we've got these satellites flying around and they're at different heights, so different orbits. I am wondering, is there any option here or any possibility of using GNSS satellites to help sort of orientate sort of lower flying satellites, lower orbiting satellites?
Yes and no. So you can definitely use them for positioning. So just so folks know, GNSS, Global Navigation Satellite System. Everybody uses them all the time on your phones and everywhere else. And there's a few different constellations of them. The U.S. has GPS. Europe has Galileo. China has Beidou. For instance, Russia has GLONASS. They are higher than most satellites, particularly most Earth observation satellites. Like I said, EO satellites tend to be low Earth orbit. The GNSS constellations, they tend to be up around 20,000 kilometers, so still lower than geostationary by and large, but still pretty high up there. So yeah, they are high enough. You can be receiving signals from them in a lot of cases, but there's a few aspects to what extent you can use them. One is error. The faster you're moving, the higher error you're gonna have when using one of those systems, when using a GPS signal. And satellites, they are moving, in fact, quite fast. Another factor is, the higher up you are, as you sort of suggested, the lower accuracy you're going to be. These satellites, they're not broadcasting omnidirectionally with equal strength. They are broadcasting specifically at Earth. So you can sort of imagine a cone going out from each of those satellites to Earth, and it's sized to really hit the entire section of Earth that they can see. And when you're on Earth, you're constantly, having overlap of at least, four or more of those satellites, because that's how GPS works. You got to do triangulation between, four or more of these. But as you get to higher altitudes, those cones are all going to be getting narrower, and you're increasingly going to be, in gaps between those cones for some portion of the time, which is also going to hurt, your accuracy, your ability to get your position. The other thing is GPS predominantly just gets you position. It typically doesn't get you attitude. If you have a single GPS receiver, all it knows is where it is. It doesn't know which way it's pointing necessarily. In order to get your attitude, you need to have two different receivers that are far enough apart from one another that they can, actually distinguish each other's signal with some kind of accuracy, which I believe has been done before, but it's not very common, and it's not really feasible on small satellites at all.
Would it be possible to put something on Earth, like broadcast out from Earth, this is Earth, a signal that would tell the satellites that as long as you can like hear this signal clearly, you're pointing at Earth?
Yes, and so ground stations for satellites actually commonly, serve this function to a certain extent. And this is also how NASA does, or part of how NASA does tracking for its various probes and rovers to other planets or to the sun. It's, you have what's called the Deep Space Relay Network. And basically by looking at, broadcast from those and receipt from those satellites, they can figure out, okay, where is Earth relative to where I am? How far away is Earth relative to where I am? That kind of thing. This is certainly possible. It gets harder the further out you go, as you might imagine. You need, higher powered broadcasters or better, receivers on the satellite end. And that's part of why when it comes to, deep space operations, across the solar system, maybe even in the future to other solar systems, people are increasingly looking at, other forms of navigation. Basically, better advances of the star trackers I described. One of the big ways is using pulsars, with these very bright, rhythmic stars. And by, if we get a map of those, they're relatively easy to detect. And you could use those to triangulate, where you are, in the galaxy, for instance.
Wow, Jack, we have come a long way in this conversation, and I really appreciate your patience. I'm sure some of my questions sound really naive, but I find this absolutely fascinating. I hope that you'll bear with me for just a few more minutes. Okay, so you talked about the deep space network just before, and networking made me think of mesh networking. So there's lots of satellites orbiting the Earth in constellations. I'm assuming that they have a lot of similarities, these satellites. Perhaps they're affected in similar ways as they orbit the Earth. I wonder, is there anything happening within constellations, any kind of mesh networking within constellations saying, hey, I'm experiencing this force on me now. When you get here, you should consider adjusting in some way, or perhaps even using them as reference points within the network, confirming that they're all still within the network?
Yes, so that is historically uncommon because, typically, satellites were, one off or just a handful, but, is becoming more common over time. One of the things that GPS satellites do, what they're doing, their primary function that you're getting on your phone is they're just broadcasting what time it is. And then, your phone looks at the differences between all of those different broadcast times it received to figure out, where those are. But of course, those satellites, they drift over time. And so one of the other things that they do is they do, in fact, broadcast like, hey, you thought I was going to be here at this time. I'm actually a little bit off that because there was some error. And so they periodically broadcast that. And that's, used by, a variety of systems. As you see more and more satellites that are standardized and large, I think you're going to see more and more of that kind of use, particularly as we move to what's called like a free space optical domain, a laser communications domain. You're definitely going to see more of that. This is basically how there's a NASA satellite called a GRACE, which measures Earth's gravitational field very precisely. And that's a pair of satellites that use a laser to measure the distance between them constantly. And by looking at how those vary from one to another, they can sort of get a sense of what's the difference in different mass concentrations, different densities on Earth at different spots to map out Earth on a three-dimensional way. I think just recently we heard an announcement that an experimental free space optical laser communication system is going to be deployed to the International Space Station. I think as you see those systems become more common, they're also certainly going to be generating a lot of data on the relative positioning of two or more satellites.
This seems to me like it's another very important use case for really deeply understanding the orientation of your satellite. So we need to understand where the sensor's pointing. Let's assume that we're talking about an Earth observation satellite. That needs to be pointing at Earth. The solar panels need to be pointing at the sun. And if there is laser communication between a pair of satellites or perhaps a network of satellites, they would really need to understand exactly where they are if they're going to hit each other with those lasers and be able to communicate.
For sure, often they're very small. We're talking, like on the order of like 8-ish centimeter diameter, these laser targets, and for two objects that are moving very fast relative to one another. So in addition to detecting where you are and where you're pointing, you have to have a very fine ability to control where you're pointing, which I guess we didn't really cover yet. So, we mentioned propulsion. Propulsion is obviously used to move yourself through three dimensions. For larger satellites in particular, it's also used for orientation. You can have multiple different rockets or thrusters at different corners of your spacecraft to turn yourself. But a lot of satellites, they don't do use that kind of thing for attitude control. Instead, they use the main thing that they use are called reaction wheels. Basically, flywheels, gyroscopes that you can spin up and slow down to change your angular momentum. It's the same kind of concept of if you've ever like spun around in an office chair with your arms out and then like tucked them in, you'll like speed up when you tuck your arms in and you'll slow down when you extend your arms. The same kind of thing by, speeding up or slowing down a wheel on your spacecraft, it'll cause it to rotate in the spacecraft as a whole to rotate in the opposite direction. And by having, typically at least three, but, usually four or more of these wheels, you can very precisely orient yourself towards wherever you need to be oriented.
Wow. So when I hear you talk about this and all of the amazing things that scientists around the world have figured out in order to make satellites possible, in order to make Earth observation platforms possible, it makes me wonder: are we done now? Is that it? Like, is this the mic drop? Have we figured all this stuff out? Is the only problem we're left with now is it making it sort of better, faster, cheaper, or what are the next sort of major problems to solve when you think about space and satellite platforms?
That's a good question. In terms of Earth observation, I do think, as you mentioned, the edge computing is going to be a big one, particularly as we move into higher data production levels. When you're talking about constellations like Planet, for instance, that are doing tons of high resolution imagery of the entire world each day. When you're talking about hyperspectral imagery, most current satellites, Sentinel 2, Landsat, they're so-called multispectral. They have on the order of 10 to 20 different bands of light that they're looking at. But there's various satellites that are being worked on right now, and some have even launched that do hundreds or thousands of bands, so-called hyperspectral imagery. It's a huge amount of data, and it's not necessarily feasible to downlink it all currently. And so I do think that that edge computing, figuring out what are the actually good images to downlink, are going to be a big thing. And then, of course, we mentioned free space optical communication, that laser communication. I think that's going to be a big one because its bandwidth is just so much higher than radio communications. So I think that'll really help with communicating from satellite to satellite, help share around some of that bandwidth. And then maybe eventually we can get free space optical for your uplink, downlink, to the surface of the Earth and transmit a lot more data that way.
So I realize that you're doing your PhD in the field in this field. You're thinking about this stuff all the time, and when you talk about it, you talk about it very sort of neutrally, I guess. Do you still have a sense of wonder when you think about how far we've come and all the things that we've accomplished? When you think about the technology and how it all fits together to give us pictures of the Earth?
Oh, I definitely have a sense of wonder. I think my sense of wonder, if anything, has only grown. Like the more I learn about satellites, the how complicated they are. Right now, I'm definitely over the past 2 years, as I've gotten really into applications of Earth observation imagery, My wonder there has really grown. This past week, actually, I spent way more time than I should have figuring out how the human eye perceives color. Because as a mechanical engineer, that was something that I never learned about. But learning more about the different light spectrums that we detect from satellites, and how what the sun emits, its interactions with the atmosphere. I got really curious about, oh, how does the human eye work? How does it interact with all of these colors that we're seeing? And so, sort of following that entire pipeline of light being emitted from the sun and coming through the atmosphere, bouncing off of things on the earth and making it into our eye, I find that immensely fascinating.
What's your dream job when you're finished with your PhD?
So I'm very fortunate right now in that, and I'm not the only one. We're living in, I think, a golden age of both geospatial data work, a golden age of space industry, particularly compared to where like my parents' generation was, for instance. And there are a lot of commercial players out there launching new Earth observation satellites, designing, building their own satellites, and a bunch of others who are figuring out new and innovative ways of processing that data and turning it into useful products for people to use for agriculture, for water, for transportation, for all these things. And I'm really excited to join one of those sort of startup companies when I graduate.
I wish you all the luck in the world with that. I really do. I have to say, like talking with someone like you that is so knowledgeable about this, it's kind of intimidating. I feel like I'm way out of my depth, but it has been an absolutely fascinating conversation, and I really, really, really appreciate your time. So there'll probably be some listeners listening to this and thinking, how can I get a hold of this guy? How can they reach out to you if they want to continue the conversation, or if they want to ask more questions or share their experience? How can folks connect with you?
Yeah, so you can definitely reach out to me on Twitter. I'm Jack B. Reid on Twitter. My email, I believe, is also on the MIT Space Enabled website. If you just Google Jack Reid, MIT, I'll probably come up there, and I'm happy to respond to any of those. And I certainly encourage people. I encourage people to learn more about this. Yes, it can seem intimidating. I don't know. For me, it's been actually going the opposite direction, and that like I've been learning a lot more about GIS over the past few years. This podcast has been a great way for me to learn about that. And so all of that was very intimidating for me for a long time in terms of like machine learning and rasters and all of that kind of data stuff. And yeah, and I've really enjoyed learning about it more. Encourage everybody to learn what it's like for further upstream. And I still find things intimidating, right? I've taken a look at like the GPS like error correction documentation, and that is immensely intimidating to me. So there's always more to learn.
Jack, once again, thank you for your time. You're an absolute legend. I really appreciated this conversation.
Thank you. And you keep up the good work yourself. It's an excellent podcast.
Thanks again to Lightbox for sponsoring this podcast episode. If you are in the US or Canada and want to locate your customers and prospects using addresses, geocoding, and property information, or if you're working in real estate, government, telecommunications, insurance, energy, or utilities, check out Lightbox. That's lightboxre.com, and there'll be a link in the show notes of this episode to make it easier for you to find. Thanks, Lightbox. Really appreciate your support. Well, I really hope you enjoyed that episode with Jack Reid, a current PhD student at the MIT Media Lab. If you check out the show notes of this episode, you'll see different ways of connecting with Jack on Twitter, and of course there'll be a link to his profile on the MIT Media Lab website. And I know that he would really appreciate it if you took the time to reach out to him. So as promised in the introduction, I just wanted to mention a few resources that you might find interesting. So if you enjoyed this conversation, it might be worth checking out a few of our previous podcast episodes. The first one I'd like to recommend is Navigating the Past, Present and Future of GNSS. You might also enjoy an episode called Satellite-Based Augmentation System, a base station in the sky. Don't let the names of these episodes terrify you. I try to choose guests that will do a great job of sort of breaking things down and explaining things to mere mortals like us. But I realize when I read that name out loud, it's like, whew, that sounds pretty heavy. It's not. It's a fascinating episode, and I think that you'll enjoy it. And last but not least, there's an episode called the Landsat Program. This is brilliant. So this is a really, really, really interesting episode about how you get a satellite into space. It's Jeff Mask, the Landsat 9 project scientist for NASA at the Goddard Space Flight Center. It does a really, really brilliant job of walking us through all the different things, all the different details of launching a Landsat satellite. It's an enjoyable episode, and I think you might appreciate it. That's it for me. I'll see you again next week. As always, you're more than welcome to reach out to me. You can find me on social media. I'm most active on Twitter and LinkedIn, and there'll be links to places where you can connect with me as well in the show notes of this episode if you're interested. We'll talk again next week. Bye.